Hello, class. In front of me, I have our lecture notes from this morning, where we talked about Lewis structures and some resonance. And so in a second, I am going to go over that material in a video, but I'd like to first explain what the purpose of these additional pre-recorded videos are. So the ideal situation is that you'd be able to come to class in person or be able to stream via the live streaming provided by Zoom. But if you can't do either of those things, coming here and watching on YouTube or Google Drive is a great way to at least stay in touch with the material. So the material that's going to be covered in these videos is going to be condensed. It's going to be at a faster pace than I would do in class, and there aren't going to be any breaks for people asking questions because it's just me talking. So the videos are going to be quick, but it is hopefully identical to the content that I cover in class. So if you miss something or if you can't attend lecture for any reason this semester, you're perfectly welcome to come here. So before we get started, for those of you who are not able to attend class, I wanted to introduce myself. My name is Chris Kodik. I'm in the chemistry department. I'm an assistant professor and I've been at Wheaton for 4 years. I also went to liberal arts college and I got my doctorate in inorganic chemistry from UC Irvine, and I did a postdoc at Boston University for 2 years before coming here to Wheaton. And I'm really happy to be at Wheaton. I really love teaching chemistry here. Aqueous is one of the classes that I teach the most, along with inorganic chemistry, advanced inorganic chemistry, and last year quantum chemistry for the first time. So I really enjoy aqueous. It's one of my favorite topics to teach because it's a really nice broad overview of a lot of the topics that are very, very important to things like biochemistry, where you have acid-base chemistry, you have electrochemistry happening inside your body all the time. There are redox reactions happening in iron inside of your lungs that allow you to break down oxygen and get the energy from that. And your blood needs to be buffered to a specific pH or, well, you'll die. So it's really great that all these things work, and they're very complex systems for things that we can't see. And as you'll see throughout the course, it's amazing how well we're able to describe them with relatively simple equations. We will be doing math in this class, but nothing more complicated than some logarithms and some algebra. So there are a few things that we're going to go over quickly about the syllabus. So the first one is that the final is optional. So on the syllabus, you'll see 2 different grading schemes, whether or not you decide to take the final or to not take the final. That'll be perfect. That'll be completely up to you, and I'm perfectly happy to allow you to not take the final if you don't want to. That just means that your individual exam scores or your problem sets will just be weighted a little bit more heavy. So later in the semester, maybe around April, we'll figure out exactly how we're going to do that. Basically, you have to tell me at some point whether you decide to or to not take the final. Additionally, there will be some group work in the future in our class once I figure out a good way of doing that remotely. My office hours, my drop-in hours are going to be remote, so you can just pop in on Zoom or on a Google Hangout, and we can chat about chemistry. And I believe that's it for now. I hope you enjoyed the class. I'm excited to be teaching it. I'm really excited to provide a in-person option. But again, if you can't attend class for any reason or if you're remote, that's perfectly fine with me also.
All right, class. So for our first topic, we're reviewing Lewis structures under the topic of chemical bonding and molecular shapes. So with our first 3 examples, we're looking at the Lewis structures for NH3, which is ammonia, CO32-, which is carbonate, and CO3b-NH3, which is a boron and nitrogen-containing compound. So in our first example, we've drawn the Lewis structure of ammonia, and that's NHHH with a lone pair on the nitrogen. So you may recognize the shape as being a trigonal planar shape. Over here, we have carbonate, drawn with a central atom carbon, double bound to oxygen, which has 2 lone pairs on it, and then a single bond to 2 different oxygens. Each of them have 6 electrons in lone pairs. And over here to the right, we have the boron and nitrogen-containing compound, with boron bound to 3 chlorines, bound to nitrogen, which is itself bound to 3 hydrogens. So as you can see, each of these atoms has already been described in terms of its formal charge. So starting on the left, we have nitrogen, and it has this circle around it to show which valence electrons are immediately in the vicinity of nitrogen. So even though it's bound in 3 single bonds to hydrogen, it has 1, 2 electrons in a lone pair, and 3, 1, 2, 3 electrons immediately next to it coming from the bonds. Nitrogen is a group 5 element, and being a group 5 element means that it is found here on the periodic table in the main group right between carbon and oxygen, being group 5. So as nitrogen is a group 5 element, it brings with it 5 valence electrons from the periodic table. And so this nitrogen here has 5 valence electrons around it in its immediate vicinity, which is exactly how many it's supposed to have, so that nitrogen is neutral, it has no formal charge. The larger ring around it shows the octet. It has 2, 4, 6, 8 electrons around it, 2 of them in a lone pair and 6 in single bonds. In our center example, carbonate, we have a carbon with 3 oxygens around it. The oxygen up top, labeled oxygen A, has 1, 2, 3, 4, 5, 6. 6 electrons around it in its immediate vicinity. Oxygen is a group 6 element, meaning that it brings with it 6 electrons from the periodic table. Its valence electrons are 2s2, 2p4, which brings you up to a total of 6 electrons. So that oxygen is perfectly happy. It has 6 valence electrons around it. It brings with 6 from the periodic table, so it is neutral. Down here, though, oxygen B has more electrons around it. So given that it has more electrons in lone pairs, we have 1, 2, 3, 4, 5, 6, and then this additional 7th one in its immediate vicinity, which is one of the ones from the bond. So given that this oxygen now has 7 electrons around it, that is 1 more electron than it's supposed to have. Electrons are anionic, so the charge becomes more negative. So these oxygens each have a negative formal charge, which is what contributes to carbonate overall having a 2- charge to the molecule. Similarly, over here with the trichloro-boroammonia compound, the chlorines, each of them are group 7 halogens. Group 7 is right here, and chlorine brings with it 7 electrons from the periodic table. Here, we see that the chlorine has 7 valence electrons immediately around it, so that it is happy with a neutral formal charge. Moving on to boron. Boron has 1, 2, 3, 4 valence electrons around it, half of each of the bonds. Now, boron is unique in that it is a group 3 main group element, so it only needs to have 3 valence electrons around it, and it is unique in that it only requires a total of 6. It disobeys the octet rule. So boron is a group 3, so it's only supposed to have 3 electrons around it, but this boron in actuality has 4 around it, giving that boron a -1 formal charge. Nitrogen from the periodic table, as we've seen already, is a group 5 element. It's supposed to have 5 electrons around it, but we're actually missing one for this nitrogen because it has 4 valence electrons around it in its immediate vicinity. So we are missing an anionic electron, which brings this charge to be more positive. So we have a +1 formal charge on nitrogen, and we have a -1 formal charge on boron. These balance each other out so that the overall species is without a charge. It is a neutral compound. So that is the shortcut for how to identify formal charges based on the amount of electrons that element brings with it from the periodic table, and you identify that based on what group number they are in. Boron's 3, carbon 4, nitrogen 5, oxygen 6, and so forth. The other way of doing it is the more long form, which is using a equation. And so the equation is shown here, which is the total number of valence electrons that atom brings with it from the periodic table, minus the lone pair electrons that are around the atom, and then you subtract half of the bonding electrons. So if we do that analysis for hydrogen, hydrogen is a group 1 element, so it has 1 electron. The hydrogens in ammonia have no lone pairs on them, so that's a 0. And each of the hydrogens in ammonia has a single bond to it. Each of those bonds contain 2 electrons. And so the total equation goes as follows. 1 electron minus 0 from lone pairs minus half of the bonding electrons, which gives it a 0 formal charge. For nitrogen, we have 5 valence electrons from the periodic table. We have 2 electrons that are in a lone pair. And we have 2, 4, 6 electrons that are in single bonds. Half of that is 3, so 5 minus 2 minus half of 6 is 0. So the formula confirms what we did with the shortcut, which is that none of these elements in ammonia have a formal charge. Moving on to carbonate. Carbon has 4 valence electrons around it from the periodic table. The carbon in carbonate has no lone pairs on it. It's only bound by localized electrons in chemical bonds. So we have 4 electrons minus 0 lone pairs minus half of the 8 electrons that are total found in bonds. 4 minus 0 minus half of 8 is 0. So that confirms that that carbon in the center has no formal charge. Now we're going to move on and look at oxygen A. Oxygen A has a double bond to it and 2 lone pairs. Oxygen brings with it 6 electrons from the periodic table, and you subtract out those 4 electrons in the lone pairs minus half of the 4 electrons in the double bond, that also gives you 0, confirming that this oxygen at the top has no formal charge. Moving on to oxygen B. Each of these has an anionic -1 formal charge. Oxygen B, 6 electrons from the periodic table, minus 6 from lone pairs, minus half of the 2 in the single bond, gives you a -1. So the formula confirms that each of these oxygens have an anionic -1 formal charge. And finally, we just did the shortcut for looking at chlorine, boron, and nitrogen in these compounds. So the shortcut confirms that, the chlorine has 7 electrons in the periodic table. It has 7 around it in the compound, so it should be 0. Boron has 3 around it, or has 3 electrons in the periodic table. Actually has 4 around it, so it's anionic. Nitrogen has 5 from the periodic table, but it's missing 1 because it only has 4 around it, which makes that positive. So chlorine 0, no formal charge. Boron -1, nitrogen +1. We are now going to talk about resonance. So resonance structures show that more than one Lewis structure of a molecule with all the atoms in exactly the same place, but with a different arrangement of electrons. So this is a really important and very precise definition for resonance structures. The moment you move an atom in space, you have actually created a chemical reaction. So every single atom has to be in exactly the same place for there to be a resonance structure. Only the arrangement of electrons is different. And that is why we use a different type of arrow that you may have seen in organic chemistry. That is the double-headed arrow going from left to right. So we have 2 criteria for the best resonance structures. So first, good resonance structure will not violate the octet rule for most 2p atoms. So the octet rule is a fantastic rule that is very, very reliable for some of the periodic table. Most of the periodic table does not participate in the octet rule, I guess. Most of the elements can have a variety of number of electrons around them, but the octet rule is very reliable for this part of the periodic table, specifically for these atoms. Boron only needs 6 electrons around it, but carbon, nitrogen, oxygen, fluorine, and neon all are happiest when they have an octet, a total of 8 electrons. And the reason for that is by having a total of 8 electrons, they become isoelectronic, having the same electron configuration to neon. Granted, that is most true in ionic compounds when you have completely transferred electrons from one to another, but nitrogen, carbon, and oxygen and fluorine, these 4 2p elements, are really good at getting close to being neon by sharing electrons in covalent bonds. So the octet rule is really reliable for the 2p elements, but once you get down to like the 3p, like phosphorus and sulfur, they don't really care about the octet rule at all. So we'll see a lot of violations of it. So the best resonance structures will not violate the octet rule for most 2p atoms. Additionally, the best resonance structures for a compound will minimize charge separation. And we see that in our first example of a resonance structure for carbon dioxide. So shown here is a Lewis structure for carbon dioxide. We have carbon in the middle and oxygen on the outside. Carbon has no formal charge on it because it brings with it 4 electrons from the periodic table, has 4 electrons in its immediate vicinity, so carbon is perfectly happy here, forming 4 bonds. Oxygen looks very similar to oxygen A from carbonate, has 2 bonds and 2 sets of lone pairs, also has a formal charge of 0. That is one resonance structure for carbon dioxide that's perfectly happy. We can rearrange the electrons, keeping all of the atoms in exactly the same place, and we get a different version where we have a single bond to one of the oxygens, oxygen A, and we have a triple bond to oxygen B. Both of these oxygens are happy in that they do not violate the octet rule. So each of these oxygens have 2, 4, 6, 8, and 2, 4, 6, 8. Both of them have 8 electrons around them. Carbon has 8 electrons around it. All of these atoms are in accordance with the octet rule. However, oxygen A has a total of 7 valence electrons immediately around it, which is 1 more than oxygen is supposed to have, so it's anionic. Oxygen B here has 1, 2, 3, 4, 5 valence electrons around it, which is 1 fewer than it's supposed to have, so it has a positive formal charge. This is not minimizing charge separation. So this is an unfavorable resonance structure because we unnecessarily have formal charges on these atoms when we have a perfectly acceptable Lewis structure that has no formal charge. Now, we can also see a minimization of charge separation in phosphate. So one version of phosphate has phosphorus as the central atom with 4 oxygens around it. Each of these oxygens, if you analyze their formal charge, you'd find that they're all anionic by -1. Phosphorus is group 5. It is right underneath nitrogen, so it's supposed to have 5 electrons around it, but this phosphorus only has 4 electrons around it, which gives way to its +1 formal charge. Now, if we donate some of these electrons into this bond and make this resonance structure, it is true that 3 of the oxygens are exactly the same, but we've minimized a little bit of this charge separation by creating a neutral oxygen and a neutral phosphorus. It does not matter that this phosphorus has more than 8 electrons around it because phosphorus is not a 2p element. Phosphorus is 3p, so it's totally fine having more than 8 electrons around it. So if you see, this phosphorus has 2, 4, 6, 8, 10. That phosphorus is violating the octet rule, but it's okay because it's a 3p element. So it's violating the octet rule, that's fine. It's minimizing charge separation, that's great. So this is actually the most favorable version of the Lewis structure for phosphate. And 1, 2, 3 anions gives way to its -3 charge on the compound. Now if we move down to our third and final example for resonance, what we can see is a couple of resonance structures for H3CCOO. This is the shorthand for acetate, which is the conjugate base of acetic acid. So over here on the left, we have one resonance structure for acetate, H3C, C double bond to oxygen, so there we have a carbonyl in the center, and over here we have an oxygen hanging out on the side. This oxygen has a -1 formal charge. This oxygen has a neutral formal charge. If we donate these electrons and push some other electrons up to the top, we get a resonance structure that looks something like this, where now we have the carbonyl on the bottom right, and we have the anionic oxygen on the top. In truth, the real structure of acetate does not look like either of these compounds. In reality, it looks a little bit more like this, the resonance hybrid, where we have that anionic charge distributed and delocalized between 3 atoms, these 2 oxygens and the central carbon. So the resonance hybrid looks a little bit more like this, and that is a more accurate version of what to expect for the compound. Next, about molecular structures, we need to discuss their shape and where the shape comes from. And that has to do with valence shell electron pair repulsion theory. And what this really is the fact that shapes are really governed by repulsion between anions and anions. Just like if you hold up the anionic end of a magnet to one another, they'll repel one another and like to be further apart. Well, that is exactly true for chemical compounds as well. except our anionic magnets are electrons. Electrons are anionic. So when electrons are near other electrons, provided that they're not in the same orbital, they will start repelling. So we see an example starting from borane. So here we have BH3, B with 3 H's attached to it. Like I said, boron is the 2p element that is perfectly capable of violating the octet rule. Boron only needs 6 electrons around it. So here we have boron with 6 electrons around it. It does not need any more, so there are no additional electrons on boron above the plane of the paper or below the plane of the paper. So this is a planar molecule, and it's trigonal, and that gives way to its shape, which is trigonal planar. Every one of these atoms is in the plane of the paper. Its polarity is nonpolar. It is perfectly symmetric. You have a BH bond in this direction, in this direction, and in this direction, all kind of pulling and flexing on each other equally. So this is a trigonal planar nonpolar molecule. However, if we start introducing asymmetry, we get something like this, which is formaldehyde, H2CO, where we have carbon bound to 2 hydrogens and a carbon bound to an oxygen. If you did the analysis, either the shortcut or the formula, you'd find that oxygen is neutral, no formal charge. Same with carbon, same with hydrogen. Oxygen, however, is more electronegative than carbon and more electronegative than hydrogen. It is right next to fluorine. Fluorine has an electronegativity of 4, oxygen 3.5. So it has a lot of electronegativity as you go to the top right of the periodic table. So there is more electron density on the top part of this molecule, which gives way to a dipole, indicated by this dipole arrow. That is to indicate that there's more electron density sort of shifting to this part of the molecule. So although the shape of this molecule, formaldehyde, is the same as borane, you have a central atom with 3 atoms around it. It's planar. There's nothing above the plane and nothing below the plane. It is actually a polar molecule. So its shape is the same, trigonal planar, but given that there's more density at the top, this molecule is polar. And that's the end of the material for our first lecture.